is this section is about matrix algebra. Turns out they have an arithmetic. You can add, subtract, multiply, divide matrices. Well, sometimes the last, and sometimes the multiply. Two matrices are called m by n if they have m rows across, and n columns up and down. The entry in A's row I and column J is A sub I J. Two matrices are equal if they have the same dimensions, m by n, and the same entries, Aij equals Bij for all I and j. Now, we're going to define an arithmetic for these matrices. If they're both the same size, A and B, then we can add, subtract, and rescale a matrix this way. The ijth entry of the sum is Aij plus Bij. So you add entries, each one parallel to the other. A minus Bij is Aij minus Bij. You can subtract entries one by one. Kaij is K times Aij. You can rescale entries one by one. So for example, you have the matrix 1, 2, 3, 4, and the matrix B, 10, 8, 9, 7. You add the matrices A by EB by adding entries. 1 plus 10 here, 2 plus 8 here, 3 plus 9 here, 4 plus 7 here, which is 11, 10, 12, 11. We subtract entries by subtracting entries one by one. 1 minus 10 upper left, 2 minus 8 upper right, 3 minus 9 lower left, 4 minus 7 lower right. So you get -9, -6, -6, -3. And twice in A is you double every entry. Twice 1, twice 2, twice 3, twice 4, therefore 2, 4, 6, 8. Okay, sometimes you get troubles with dimensions not matching. Here we have matrix A, 2, -5, 0, 7. B is 3, 12, 3, 1/2, 5, 1, -1, 3. And C is 2, -5, 1/2, 0, 0, 2, -3. So, for example, say, what is 5A? Well, you multiply each of these entries by 5. 5 times 2 is 10. 5 times -5 is -25. 5 times 0 is 0. 5 times 7 is 35. So this is the matrix 5A. Now, C minus 5A. Well, C is 2 by 3 and 5A is 2 by 2. The dimensions don't match, so you can't really define their difference. B plus C are the same dimensions. They're both 2 by 3. So you can add them by adding entries. 3 plus 2 is 5. 1/2 plus -5 halves is -2. 5 plus 0 is 5. 1 plus 0 is 1. -1 plus 2 is 1. 3 plus -3 is 0. That's the sum. B minus C, you can add, subtract entries. 3 minus 2 is 1. 1/2 minus -5 halves. After a bit of arithmetic, that's 3. 5 minus 0 is 5. 1 minus 0 is 1. -1 minus 2 is a -3. And 3 minus -3 is a 6. Now, multiplying matrices is rather more complicated. We start with a row vector, a matrix, a 1 by n matrix, with a column vector, an n by 1 matrix. A is A1, A2 up to AN, B is B1, B2 down to Bn. And we multiply these two by multiplying A1 times B1, A2 times B2, A3 times B3, all the way up to AN times Bn, like that. So you multiply entries and then sum the results. For example, 137 times 246. That's 1 times 2 plus 3 times 4 plus 7 times 6. And after some arithmetic, it's 56. Incidentally, this is not really a number. This is a 1 by 1 matrix. And if you have an m by n matrix and an m by p matrix, and this m has to match this m here, you can multiply them by multiplying A's rows by B's columns. So the ijth entry of AB is A's row I times B's column J. So AI1, Bij, BI1, B1J, AI2, B2J, all the way up to AIN, BNJ. For example, here's the matrix 2, -5, 0, 7, and the matrix 3, 1, 2, -1. We'll multiply them. Well, first of all, they're both 2 by 2, and the 2's match up. Here we go. We divide up A by rows, we divide up H by columns, and we multiply accordingly. So AH is upper left column is A's upper row times J's H's left column. 2 times 3 plus -5 times, oh dear, this should be a 2. I get so honked. I am so sorry. This is page 5, page 2, page 5, AH blunder. So I'll have to change that in the canvas after this. The upper right entry is the upper row times the right column, 2 times 1 plus -5 times -1 here. Lower left entry is lower row times left column, 0 times 3 plus 7 times 2. Lower right column is 0 is lower row times right column, 0 times 1 plus 7 times -1 is there. Okay. And you do the arithmetic, it's 1, 7, 14, -7. Now, if you do HA, multiply these in the opposite order, things get a little strange. Okay, we divide H by rows and A by columns. Upper left entry is 3 times 2 plus 1 times 0 here. Upper right entry of the product is upper row of H times right column of A. 3 times -5 plus 1 times 7 here. Lower left entry of HA is the lower row of H times the left column of A. 2 times 2 plus -1 times 0. And the lower right entry is lower row of H times the right column of A. 2 times -5 plus -1 times 7 here. And after some arithmetic, it's 6, -8, 4, -17. And notice that these two are not even remotely the same. So AH is not necessarily equal to HA. I mean, sometimes that works. It's called commutativity. But it's not like multiplication of ordinary numbers where A times B is always B times A. Not so in this case. So matrix arithmetic lacks what they call commutativity, though it has a lot of the other usual rules. Here we have A is 2, -507, is B is 314,721. This is 2 by 2, and this is 3 is 2 by 3. It matches up if you do A times B. Number of rows equals a number of columns for A equals the number of rows for B, so it matches up. Divide up A by rows and B by columns. And upper left, 2 times -5 times 3, 7. 2 times 3 plus -5 times 7. Upper middle entry is upper row of A times middle column of B. 2 times 1 plus -5 times 2. Upper right entry of AB is upper row of A times the right column of B. 2 times 4 plus -5 times 1, like that. Lower left entry, lower row, left column, 0 times 3 plus 7 times 7. Lower center is lower row times center column, 0 times 1 plus 7 times 2. Lower right entry is lower row times right column, 0 times 4 plus 7 times 1. And after the arithmetic, -29, -8, 3, 49, 14, 7. Okay. Now, if you try BA, here's the problem. B is a 2 by 3 and A is 2 by 2, but these don't match up, so the product is undefined. So a lot of matrix arithmetic isn't properly defined because they don't match up. Here we have a 3 by 2 times a 3 by 2. 2 and 3 don't match up. Too bad. But here's a 2, 1, 2, 6, 3, 4, 1, -2, 3, 6, -2, 0. This is 2 rows by 3 columns. This is 3 columns by 3 rows by 2 columns. 2 by 3 and 3 by 2. These match up. We do all the products of rows and columns. You can get a 2 by 2 matrix, 1, 2, 7, 6. Here we have a 2 by 2 times a 2 by 3. These two match up, so you can work it out and get this 2 by 3 matrix. Here's a special kind of matrix, 1001. It times A, B, C, D. Either way, it comes up to be A, B, C, D again. Upper entry, AB times 1, 0, 1A plus 0B is A. Upper right entry, AB times 0, 1, 0A plus B1 is B, and so on with the rest. And it works in both directions. This matrix 1001 is called I2, the 2 by 2 identity matrix. Multiplying it by a 2 by 2 matrix keeps it the same, that other matrix the same. So this is sort of like the matrix version of multiplying by 1. Here's I3, 100 or 1001. It's a 3 by 3 identity matrix. If A is 3 by 3, then AI3 equals I3, A equals A. And IN is a matrix with ones, is an n by n matrix, ones down the diagonal, zeros everywhere else. And if A is n by n, then A times IN equals IN times A equals A. So we have the matrix equivalent of multiplying by 1 in all n by n matrices. Right, here we're trying to find the powers of a matrix, second and third power. Well, that's just repeated multiplication. 5024 is 5024, 5024. After doing the arithmetic, let's see, first row times left column, 5 times 5 is 25, plus 0 times 2 is 0. Upper right entry, upper row times right column, 5 times 0 plus 0 times 4 is 0 plus 0. Lower left, lower row times left column, 2 times 5 plus 4 times 2, that's 10 plus 8. Lower right, lower row, right column, 2 times 0 plus 4 times 4 is 0 plus 16. So 25, 0, 18, 16. The third power of that same matrix is the second power times 5024. We put back 25, 0, 18, 6 times 5024. And after using the rules, you get 125, 0, 122, 64. Now, matrices have an arithmetic, and this arithmetic has equational identities. And a lot of the ones you're familiar with still apply. Adding matrices, it doesn't matter. I mean, if you can define A plus B, then A plus B is B plus A. And similarly, you get associative rule. A plus B plus C is A plus B plus C. Fine. Multiplying by a number, a scalar, C times the A is CD times A. And C times A plus B is CA plus CB. So you have associative rule and commutative rule and this version of the distributive rule. If you can define the matrices A, BC, and AB, and ABC, and so on, then associativity applies. A times BC equals AB times C. The distributive law applies. A times B plus C is AB plus AC, and A plus B plus C times A is BC plus CA. However, the commutative law does not necessarily apply to matrices. AB does not always equal BA. So that's that for that.